In this video, we're going to take a look at another class of series that can be evaluated by inspecting their partial sums. These are going to be the telescoping series. We need to define a telescoping series. So let's recall that a telescoping sequence is one where each term can be written as the difference between two consecutive terms of another sequence. So in other words, if we look at the sequence a sub n is 1 over n minus 1 over n plus 1, we can see that each term is the difference of two other terms. That sequence becomes 1 minus 1/2, 1/2 minus 1/3, 1/3 minus 1/4, and so on and so forth. When we decide to add the terms together in our sequence, it turns into a series. This series can be written as the sum from n equals 1 to infinity of 1 over n minus 1 over n minus 1. Just as we've seen before with telescoping series, we're going to evaluate them by using the limit of their partial sums. The nice thing about telescoping series is that because of the way they're structured, many of the terms cancel out so that their partial sums are easy to evaluate. Let's take a look at the partial sums for our example. So if we consider s sub n, we know that's going to be s sub 1, which is 1 minus 1/2. So that's when n is 1. Then we're going to add 1/2 minus 1/3 when n is 2. We're going to work our way all the way out to when at n minus 1. So we're going to have 1 over n minus 1. Minus 1 over n minus 1 plus 1, which is going to be 1 over n. And then our last term is 1 over n minus 1 over n plus 1. Notice in here that the terms cancel each other out. So all of the terms in the middle are going to cancel out because of the changes in sign that we're seeing. And so this is going to be equal to 1 minus 1 over n plus 1. And we can simplify that. We can get a common denominator, that's n plus 1 over n plus 1 minus 1 over n plus 1, which is n over n plus 1. And then if we look at the limit as n approaches infinity of our partial sum, that is the limit as n approaches infinity of n over n plus 1, and we know that this is exactly equal to 1. Now, unlike geometric series, for telescoping series, there is not one general formula that will allow us to evaluate them. Instead, we have to learn to recognize a telescoping series and then evaluate the partial sums on an individual case-by-case basis. So let's look at a few more examples of these. We'll start with this example here, the sum from k equals 1 to infinity of 1 over k plus 6 times k plus 7. Now, at first glance, there's no subtraction in this, so it may not look like a telescoping series. But let's see what happens when we use partial fractions in order to split this up into two fractions. So if we look at the expression 1 over k plus 6 times k plus 7, partial fractions tells us that we can write that as a over k plus 6 plus b over k plus 7. And when we use our method, we're going to get that a times k plus 7 plus b times k plus 6 has to equal 1. That comes from multiplying both sides by the denominator on the left. Now we can let k be equal to -7 because we know that this expression has to hold true for every value of k. So when k is -7, we get a times 0 plus b times -1 is equal to 1, which tells us that b itself must be -1. Now maybe we have some insight into where that subtraction is going to come from. If we let k be -6, then we're going to get a times 1 plus b times 0 equals 1, so that a is equal to 1. So this expression now becomes 1 over k plus 6 minus 1 over k plus 7. so that our original sum, the sum from k equals 1 to infinity of 1 over k plus 6 times k plus 7 is equivalent to the sum from k equals 1 to infinity of 1 over k plus 6 minus 1 over k plus 7. So let's see now what sense we might make of the partial sums for this. So let's look at the nth partial sum. That's going to include our first term, which is 1 over 7 minus 1 over 8. That's when n is 1. Our second term would be 1 over 8 minus 1 over 9. We'll go out to the end when we are doing the n minus 1 term. That's going to be 1 over n minus 1 plus 6 minus 1 over n minus 1 plus 7. And then we'll look at the last term, the nth term. That's going to be 1 over n plus 6 minus 1 over n plus 7. I'm going to do a little bit of tidying up on those last few terms so that it really becomes obvious to us which terms are canceling. So I have 1/7 minus 1/8 plus 1/8 minus 1/9. I get out here and I have 1 over n minus 1 plus 6 is n plus 5 minus 1 over n plus 6 plus 1 over n plus 6 minus 1 over n plus 7. And we see here that all of our inside terms are going to have a positive and a negative version of them, except for the first and the last. So our nth partial sum becomes 1/7 minus 1 over n plus 7. We're going to do some algebra, get a common denominator. That becomes n plus 7 minus 7 over 7 times n plus 7, which is n over 7 times n plus 7. And we have to remember that our sum, our original sum that we started with, is the limit as n goes to infinity of its partial sums, which is the limit as n goes to infinity of n over 7 times n plus 7, which is 1/7. This step's not really necessary, but I'm going to do it just in case that 7 in the bottom is muddying things up for you. So we have the limit as n goes to infinity of n over n plus 7, which is 1. This goes to 1, so we end up with 1/7 as our final answer. We'll wrap up with one more example. The sum from j equals 1 to infinity of the natural log of j plus 1 over j. Now again, like the last one, at first glance, you might wonder, how is this telescoping? There's no subtraction in there. What's going to cancel? But if we rewrite this using what we know about logarithms, we might start to see what's going on here. So we have j plus 1 over j. But we have to remember that that can be rewritten as the sum from j equals 1 to infinity of the natural log of j plus 1 minus the natural log of j. So now if we consider our nth partial sum, we're going to have the natural log of 1 plus 1, that's 2, minus the natural log of 1. And then when j, that's when we're taking n equal to 1, the first term. The second term would be the natural log of 3 minus the natural log of 2. We can continue this all out till we get to, let's say, the n minus 1 term, where we would have the natural log of n minus 1 plus 1, so that's n, minus the natural log of n minus 1. Swing around here for our nth term. That's going to be the natural log of n plus 1 minus the natural log of n. Now, our subtractions haven't fallen as nicely in order as they did in the previous examples where they were right next to each other, but you can see here I've got a positive natural log of 2 and a negative natural log of 2. Those cancel. I'm going to end up with a positive natural log of 3 and a negative natural log of 3. Here I have a positive natural log of n and a negative natural log of n. Those cancel. So all of our interior terms cancel with the exception of 2, and that's going to be this one and this one. So our partial sum is going to be exactly equal to the natural log of n plus 1 minus the natural log of 1, which is of course 0. So we see that our nth partial sum is going to be the natural log of n plus 1. Our original series, the sum from j equals 1 to infinity of the natural log of j plus 1 over j, is then the limit is equal to the limit as, doesn't matter if I write j or n here, I'll go stick with j, as j goes to infinity of the partial sum, which is the limit as j goes to infinity of the natural log of j plus 1. But the natural log is a always increasing function, which means that that limit is infinity, so that our sum or our series diverges in this case.